In this video, we're going to review the SN2 reaction, as well as take a look at some synthetic schemes that involve acid-base reactions and SN2 reactions as part of the same process. For this slide, we have already looked at the retention versus inversion of configuration at stereocenters in an SN2 reaction. And in this case, you can see that considering the two products that are possible in an SN2 reaction that involves a stereocenter, the two possible products would be enantiomers of one another. Because there are only two possibilities whenever you have a four atom chiral center, which is what chiral carbons are, it means that there are only two possibilities. And for the case of an SN2 reaction, there is the possibility of the retention or the inversion of stereochemistry. And because of the nature of the SN2 reaction, that is the backside attack of the nucleophile, SN2 reactions always do involve the inversion of the configuration at the stereocenter. We also took a look at this slide before, but I'd like to look at it in just a little bit more detail and draw a picture of what the transition state is going to look like. And before I do that, I'm going to pause and move this over. Well, instead of moving it over, I just moved it down a little bit to give myself a little bit of room. But if you take a look at this carbon here, I'm going to go ahead and draw this carbon at this position. And then if you look at what's happening, it is starting to make a bond to the thiol group, and the iodine is in the process of leaving. Well, what that means is that this has to go through an sp2-like intermediate, and so we have our ethyl group here. So CH2, CH3. And then these both started out in the plane of the paper, or in the plane of the screen. This is also in the plane of the screen because this bond, as we said, is breaking as this bond is forming. These two, however, are still coming out toward us and going back away from us. So I'll draw my methyl up here, coming out toward us, just like it is in the original structure. And then I'll draw the iodide, the hydrogen, going back away from us, just as it is in the structure here. And what you can see is as this process is taking place and the groups are all moving to point over in this direction, there is an inversion of stereochemistry taking place. If you actually do go through and assign priorities here, and we could do that very quickly, this would be A, this would be B, and this would be C. This is the S isomer. Whereas if you look over here, this would be A, this would be B, and this would be C. And if you go around, you see we're going clockwise, so this is the R isomer. So we do indeed get that inversion of stereochemistry. Now, you may have a little more trouble seeing why, indeed, this is also an inversion of configuration. And if you are having trouble seeing that, I am going to go through the transition states here in just a second. But what I'd like to point out is, just like we were talking about on the previous slide, that there are only two possibilities for stereochemistry at any chiral carbon. If we have one stereochemical configuration here, and an inversion takes place, it must be the opposite. So if these groups, the propyl and the methyl group, are staying in the same orientation in space, or on the screen, then the chlorine and hydrogen must then be switched with respect to the OH and the hydrogen, because that OH is displacing the chlorine as the hydrogen would transition over to coming out toward us. If you wanted to look at this in terms of the transition state up here, it would probably be helpful to move this chlorine down then to be in the plane of the screen. So I'm going to go ahead and do that and draw it over here. When I move the chlorine to be in the plane of the screen, what that means is that this methyl group, because I'm rotating this out further toward us in order to make it go down, because remember, if you were looking at this, say, from a Newman projection, as we rotated this 120 degrees, if this was out and to the left, this would then be down and in that same plane as the rest of the molecule here. So now, if we think about our methyl group going away from us, then the hydrogen is indeed coming out toward us. And so if we think about the transition state here and the OH coming into attack, in that backside trajectory, let's go ahead and draw a transition state here. So I'll go ahead and put the brackets with the transition state symbol. And I'm going to go ahead and draw this propyl group pointing down, just to keep everything kind of in the same orientation that you saw above. Now, instead of drawing out or writing out the letters, I'm going to draw out the propyl group. So there's our 3 carbons. I did forget up here to actually put in my hydrogen. So I'm going to go back and do that. That was the hydrogen. This was the methyl group. So now, going up and away from us is still that methyl group. Going up and coming out toward us then is the hydrogen. So all I've done here is rotate this ever so slightly so that this is pointing down. But now, because the new bond is forming from the OH and the old bond is breaking to the Cl, at the top of the transition state, or at the top of the energy barrier, what we would see is that we have an an sp2-like transition state, where this bond is breaking forming as this bond is breaking, and we're flipping this over from being these pointing off to the left to, in the product, they'll be pointing off to the right. So let me go ahead and draw that way. So we'll have then our propyl group very much like it is in this drawing. And then our hydrogen is still coming out toward us, but is pointed out over to the right instead of over to the left, as it would have been initially here. Our methyl group is going away from us, and then now, I forgot to draw the hydrogen again, and now our OH is over here. And so if you look closely at this, these are indeed the same compound. It may not be obvious to you, though, that they are the same compound, because we might need to do a couple of rotations. The first rotation that we might want to do is to think about, and you may have to tilt your head ever so slightly to the right to think about this as our straight chain alkane. What we can think about is this OH group rotating out toward us as this methyl group comes down into the plane, so that we can show our 5 carbon pentane chain. And so now I'm going to show this just as a rotation. Remember, that circle means we're doing a rotation. And so we've got a 5 membered pentane chain. The methyl group has rotated down into this direction, which means that the OH has rotated out toward us. If the OH is rotated out toward us, now the hydrogen is going back away from us. Well, now you might look at this and say, oh, well, these are enantiomers, but they're not, because if you look closely, this OH is going away from you, when it is just one carbon from the end, and this one's coming out toward you. So what we'd have to do is actually rotate this perpendicular to the plane of the paper, where this side of the molecule, you can imagine, comes out toward us. This side of the molecule comes back, or goes back away from us, and now we will rotate it one more time. Or we will have rotated it back into this orientation. So now our OH is going away, and our hydrogen is coming out toward us. So these two now are indeed the same structure. Now, I do not suggest that you do this for every SN2 reaction to evaluate the stereochemistry. What I'm showing you here is how we can justify that the inversion of stereochemistry does in fact take place, and how we can represent that. All we have to do is simply invert the stereochemistry at the position where the SN2 reaction takes place. You do not need to go through this whole process. The only time that you really need to show the transition state is when I ask you to do so, and it's likely that I will ask you to draw one transition state on the coming exam. All right, so let's move on and take just a quick look at a couple of SN2 reactions and the stereochemistry that is involved with them. So, let me get rid of that. Okay, so let's consider the reaction of R2 bromopentane. So I'm going to go ahead and draw my structure. Actually, let me clear that and do it in yellow. So if it's a pentane molecule, it would be this structure. If it's a 2-bromopentane, I can draw bromine at either end. I'll just go ahead and draw it down at this end. And now, if I need it to be the R stereoisomer, rather than drawing in whether this should be a wedge or a dash initially, I'm just going to indicate that indeed, for this group, or for thinking of these three groups, this is going to be the highest priority because it has the highest molar mass. The propyl group over on this side is going to be the second priority, and this one is going to be the third priority. Now, if we trace these around to the left, we would see that we're going counterclockwise, which means that if the bromine were coming out toward us, this would be the S configuration. However, if the bromine were in fact going away from us, and let me go ahead and draw that in now. If the bromine is going away from us and we're tracing around to the left to suggest that this would be S, we have to remember that the bromine is actually going into the plane, which means a hydrogen, which is the lowest priority group, is coming out toward us. Keep in mind that when that happens, it just means that it's the reverse stereochemistry, because when we're trying to assign R and S, we want the lowest priority group going away from us. So if it is coming out toward us, then that must mean that it's the opposite. So this is R2-bromopentane. Now, this is going to react with the hydroxide ion, OH minus, and in that process, the stereochemistry is going to be inverted at this position. And so then our final product is going to be an OH group coming out toward us. Now, in this case, you wouldn't have to draw the byproduct of bromide, but if you want to, go right ahead. But if you do try to assign stereochemistry here, it should be pretty easy to see that with this being A, and this being B, and this being C, we do now, in fact, have the S stereoisomer. So now let's take a look at the inversion of stereochemistry that takes place when you have a ring. So in this case, we have cis-1-chloro-3-methyl cyclopentane, this structure here, and a hydroxide ion is coming in, doing a backside attack so that the chlorine leaves. When this happens, this hydrogen just gets shifted up, and so now you can see the hydrogen pointed up, whereas the OH is now pointed down. And so whereas we had the methyl and the chloro on the same side of the ring, we see that it's now on opposite sides of the ring. So I was originally going to do a evaluation of acid-base followed by SN2 reactions in this video, but I've decided I will put that in the next video.